So in the previous video, we described the nature of acidic and basic solutions. And then essentially what makes something either acidic or basic is the relative amounts of H3O plus, which is the hydronium ion, versus hydroxide ion in the solution. All right. If we wanted to give a practical way to describe how acidic or basic something is, we basically want to take this information and turn it into something that would be numeric, all right, or a quantitative way of doing that. And that's what the pH scale is, all right? So if you were to say to somebody, well, how are we going to express these relative amounts of H3O plus and OH minus? You might think that just reporting the molarities themselves would be a good way, all right? But first of all, reporting both of these would be unnecessary. Sometimes you might say that it's redundant, all right? And that's because of this seesaw nature of the amounts. All right, when one is low, the other is high. Or sorry, when this would be the high one, this would be the low amount. All right. So the thing is, since there's this seesaw nature, simply reporting the amount of one of them would also communicate the amount of the other. All right. It's a little bit like if you were to report the percentage of males in a population, well, you wouldn't also have to present the percentage of females, because simply presenting the percentage of one would also communicate the percentage of the other. All right. Another issue with reporting both of these, the molarities of both of these, and actually when I'm doing this, I should have these square brackets around those to indicate that what we're talking about is the molarity of these things. All right. So the other issue is the vast range of molarities that you can have. All right. We're not really used to, in most cases, when you think about like the number that you have when you have the highest number you can think of versus the lowest number, you generally, the decimal point only moves a couple of digits. All right. But the difference here between a high H3O concentration would be about 0.1 molar. Low would be this number right here. All right, that's a decimal, and then it's got 13 zeros before you finally get to that 1. All right, that is a huge range. That is about a 10 to the 14th. One of these is 10 to the 14th larger than the other. All right. And that's not a very it's a very difficult, these are very difficult numbers to deal with. And so what we've done is we've decided to express this in a little bit of a different way, and that's to use a logarithmic scale. All right, so this is the way it works. All right, let's say that the actual molarity of your H3O plus were to be 0.1. All right, well, another way of saying that in scientific notation would be 10 to the negative 1. All right, what we're going to do is, instead of representing it like this, we are going to say that the pH is 1. All right, and one thing that you'll notice is that the pH is going to be essentially the negative of that exponent right there. All right, which typically tends to be a negative number. All right, so and I think that you guys know that if you had a pH of 1, that's going to be an extremely acidic solution. All right. Well, what if this was the molarity of our H3O plus? All right, this would be as a decimal, this would be as scientific notation. All right, well, the pH would be 7. All right, and you can see that is the negative of that exponent right there. All right, that's going to be a neutral solution. All right, and same thing here. So for a very small amount of H3O plus, which we could represent this way, all right, and essentially, by the way, what does that negative exponent mean? That's essentially the number of times that you would have to move that decimal point to get it after the 1. Notice that I have to move that decimal point 1 time to get it after the 1. That's why that's a negative 1 there. All right, I'd have to move it 7 times to do this. All right, so anyways, if we had these numbers right here, the pH of that solution would be 14, and that would be an extremely basic solution. All right, one thing that I want to point out is that if you had at a pH of 7, not only would this be the amount of H3O plus, that would also be the amount of OH minus. All right, and that's when you have that neutral solution. All right, so why do we do this? All right, well, the benefit of doing this is that we can now report how acidic or basic something is by using numbers between 1 and 14, all right, rather than 0.1 to point, and you can imagine having to list off all of these zeros, all right? And if you think about it, if you were to accidentally drop one of these zeros, remember your number changes tenfold, all right? And that's not a trivial difference. That is a significant difference, all right? And so by doing this, you're also less likely to make a mistake like that, all right? So I do want to point out that this can be a little bit confusing at first, because when you have a high H3O+, all right, so compare these numbers right here, this versus this, all right, which is the higher number, all right? Well, 0.1 is a lot bigger number than this number is right here, all right? But notice what that does in terms of its pH. The high H3O+ gives the low pH. And the reason for that is that the pH is most directly related to the absolute value of that negative exponent. All right, a large number has a relatively small negative exponent right here, whereas the small number has the relatively high negative exponent right here. And if you're taking the absolute value of those negative exponents, you're going to see that like what's high in terms of the bigger numbers here are going to give the lower pHs. All right, so it takes a little bit of time to get used to that, but you will get used to that. All right, so mathematically, how do we do this? All right, so the formula for this is that the pH equals the negative log, and when I write it like this is log base 10 of the molarity of H3O+. All right, and this is sometimes written as pH equals the negative log of just H+. In fact, if you look at if you look in your reference guide at the formula sheet, you'll notice that the formula for pH is given in this form right here. All right, I actually prefer this form right here because, again, there really is no such thing as dissolved H+ ion. You really have dissolved H3O+ ion. All right. There's also a similar measurement called POH. All right, and while I would think that most people have heard of pH, POH might not be something that you've heard of, but it does the exact same thing. All right, where instead of focusing our description of how acidic something is by telling you something about the amount of H3O+, POH tries to tell you how acidic or basic something is by telling you how much of this there is. All right, so the equation for that is that the POH equals the negative logarithm of the molarity of hydroxide ion. All right, these two equations are related by this relationship right here. If you ever take the pH of a solution plus the POH of a solution, that's going to give you 14. All right. So if you wanted to describe how acidic or basic something is by using the POH, you could do that. The thing is, most people generally like to adopt one way of talking about things, and people have just chosen to talk about pH or acidity in terms of pH because we get very used to what the numbers mean. When you hear the pH is 1, we very quickly associate that with a very acidic solution. All right, and if you went back and forth between pH and POH, you would have to think, well, what does that high versus low number mean? So we generally just stick to one way of describing this, and for most people, that's going to be talking about pH.